This question asks, consider the 3 sets of alcohols below, and each set indicate which alcohol is the most acidic. So this is really like an acid-base question, but it's applied towards 3 different sets of alcohols. This question is pretty difficult because instead of just evaluating 1 pair, we're evaluating 3. So 3 different sets to compare. And if you take a look at sets 2 and 3, we're going to probably have to use some resonance out there. If we think about CARIO, our acronym for qualitatively assessing an acid or base, a base, we can think about charge, atom, resonance, induction, orbital. And so set 1, the biggest difference there is a halogen. So that's probably an inductive effect. But sets 2 and 3 have that aromatic ring present. And so a big idea there will be resonance. So how do we go about solving this problem? First, you want to draw in the conjugate bases. And so you'll want to kind of look at the conjugate bases and compare them since we're using the qualitative method here. So we'll go ahead and do that. There's not a ton of space on this slide, so I'm probably going to have to like erase and then come back in each of these examples. So I'll kind of walk you guys through each set and how to analyze them. We'll also get a lot of practice drawing resonance contributors. All right, so for set number 1, we have a bromine and we have a chlorine. And the key difference here is basically going to be which one is more electronegative. So if we think about the periodic table, chlorine is more electronegative than bromine. Okay, and so why is that important? If we think back to CARIO, a conjugate base is going to be stabilized by a very electronegative atom. So if we draw out our conjugate bases here, the atom in each case has the negative charge on an oxygen, so they're equivalent there. But bromine and chlorine and their electronegativities can still play a role through induction. And for induction, we're going to be pulling electron density through the sigma bonds. Okay, so the idea here is just that the electron density gets pulled a little bit larger or in a higher amount towards the chlorine atom, which is more electronegative. The bromine also can have an inductive effect, but it's not as great as the chlorine because it's less electronegative. So what does that mean? It means that this conjugate base is more stable. And so we have to kind of think back to what does that imply about the acid it came from. The more stable the conjugate base, the stronger the acid that it came from. So that means acid 2 is the stronger acid. So if we're thinking about which alcohol is the most acidic, it's going to be 2 because a strong acid is a acidic acid. All right, so in this instance, I'm going to go ahead and delete or wipe away kind of our markings here so that I can have some space for solving set number 2. All right, but I will note here that 2 is the stronger acid versus 1. So set number 2 really comes down to resonance. So if we draw out what our conjugate base is, we have this guy, right, where our acetyl group is kind of out on the 3 carbon. If we were to number it, for example, we'd call that the meta position, versus the right-hand side, where our conjugate base has the acetyl group in the 4 position, or the para position. So the key here is which position is better for that acetyl group to be in resonance-wise, 3 or 4? And to figure that out, you really need to draw the resonance contributors. Okay, so let's go ahead and do molecule 3 first. I'm going to try and pick a different color here for my arrows. This will give us negative charge here. Oops, sorry about that. We pushed it down, so we have a double bond there. Okay, and then that doesn't really help us a whole lot with kind of thinking about the significance of the acetyl group. So we're going to kind of keep pushing the electron density around. This gives us this molecule, oops, sorry, I put the negative charge in the wrong spot. Right here. Okay, that also, again, not helping us a whole ton because we're not quite sure, you know, what is the significance of the acetyl group. So let's draw one more, and that will hopefully help explain this a lot more. I'm going to draw one more resonance contributor. We can kind of see that that acetyl group that's right here, oops, sorry, I'm coming off the page. Let me make it a little bit more to the right. This acetyl group that's right here doesn't really play a significant impact in the resonance contributors. It means that in the previous step, we essentially completely bypassed this carbon because of the allylic negative charge resonance pattern. We are never going to have the negative charge at that kind of orange carbon. And so the significance of that is the acetyl group doesn't help stabilize the anion at all. It's just kind of there. Right, and from that we would get back to the original starting molecule, which would look like this. So we just get back to the original base that we had with the acetyl group coming off over there. Right, in contrast, let's take a look at what would happen with the acetyl group at position 4. So if we kind of use the same patterns, whoops, I'm gonna again use purple arrows here for resonance. You would get this first pattern. And let's draw another resonance contributor. And in this instance, we have, oops, we have a little bit of a different scenario. Here, the negative charge is on the atom that's adjacent to the acetyl group. And we can see another resonance pattern because of it. We can push the electron density out, in this instance, onto the acetyl group. And this is really important for determining, you know, stability here because we have an extra resonance pattern. So this resonance contributor right here is kind of the key difference between molecule 3 and molecule 4. Molecule 4 can push the electron density out onto the acetyl group because of its position on the aromatic ring. So that's really important because it means that molecule 4 is more stable than molecule 3 because it has an additional resonance contributor. All right, so that's kind of how we solve 3 versus 4. It took a lot of arrows. It took a lot of resonance contributors to kind of visualize that. So sometimes, like a really involved question like this, you might have to really think it out and push your arrows. Okay, so molecule 4 is going to have the more stable conjugate base. So I'm going to go ahead and kind of make room for that last question. We have set 3. So for set 3, we have 5 versus 6. And both of these alcohols have a substituent on the 4 position. One has an amino group and one has a nitro group. So what role do those play? Again, drawing out the conjugate bases is going to be super duper helpful here. So I'm going to do it for the base that has the amine on it first. Let's use a different color for the arrows. All right, I'm going to get another one out here. Whoops, I skipped a step. Let me make sure I draw it all out. Okay, I have another resonance contributor. And this one sees the negative charge adjacent to the amino group. And so here we have a -1 formal charge right next to a lone pair. Okay, and if you think back to kind of first semester topics, we can realize here that a lone pair adjacent to another lone pair, which is what that formal charge is representing, is not very stable. You have kind of two negative charges right next to each other. And so that's actually a little bit destabilizing. So that kind of gives us a little bit of a hint right off the bat about 5 versus 6. Okay, well, let's draw out the resonance contributors for 6 too, just to kind of prove to ourselves that 6 is actually going to be the molecule that's going to be more stable when we look at its conjugate base. So let's draw out its conjugate base right here. And it's really important too to think about, what does the nitro group look like? So the nitro group looks like this. When we draw the resonance contributors, we get this guy. And then we can move it over. So just like in the previous case, we're going to have the negative charge adjacent to that 4, or on that, directly on that 4 position. Okay, but if you see here now, we can actually move this negative charge out onto the nitro group, kind of similar to what we did in set number 2. The nitro group is kind of an electron withdrawing substituent, and so we can push electron density out onto that substituent. So I'm going to make a really long arrow here because I ran out of room. I'm going to draw out what it looks like when we push electron density out onto that nitro group. We have the N was still +1 charge, but now both oxygens are negatively charged. And so this is kind of the key resonance contributor that shows how that nitro group is stabilizing, because it's pulling the electron density away towards itself. We can actually push it out onto the nitro group. And so that's going to be, again, an extra stabilizing resonance contributor. So more resonance contributors for molecule 6 versus molecule 5. All right, so if we think about that, 6 is going to be the stronger acid. All right, so we've looked at all of our options. Let me go ahead and erase so that we can kind of think clearly through our answer choices. All right, so we've got 2, 4, and 6 is what we thought would be our strongest acids. And let's look at the answer choices. The only one that we can say for sure that's going to work is B. Set 1, 2 is more acidic. Check. Set 3, oops, oh my goodness, that was bad, my bad. Let's take a look at that. I was wrong because that one has 3. We want one that has 4 here and 2 here. So B doesn't work. Let's look at this. C, set 1, 2 is more acidic. Set 2, 4 is more acidic. And set 3, 6 is more acidic. So C is the correct answer choice here. If we move through all 3 sets, all right? So definitely keep your eye out for resonance. Keep your eye out for whether or not you can push the resonance out onto the substituents of an aromatic ring. All right,